version of the International Inverse Problem Seminar. So we are happy. Today we have Fernando Vasquez from Utah joining us. Thanks for coming, Fernando. The talk will be about active thermal cloaking and mimicking. So the floor is yours.
All right. Thank you, Knut and Katja, for putting together this series of seminars and for the opportunity that you give me to talk about this work, which is a little bit tangential to inverse problems, but it's still related. So this is work in collaboration with Maxence Cassier, Trent De Giovanni, who is at the University of Utah, and Sébastien Guenot, who is at Imperial College London physically. And it started when, I went to visit Maxence at the Institut Fresnel, where he is now. And I, met Sébastien Guenot for the first time, and we started talking about some past work I had done on active stereo clocking for the Homos equation. And he asked me, "Oh, is this? Have you tried doing this for the heat equation?" And I said, "Well, why would you? Is it any interesting?" And then we kept digging, and there are actually interesting things in there to look at, and that's what I'm going to show you. Can you see my cursor here, by the way? Is it to point things?
Yes, we can see it.
Perfect. Thank you. So before I tell you what it means to cloak something, I should tell you with heat equation, we should settle the question on how to detect things with the heat equation. So this is a very intuitive way of explaining that. So what I have here on the left is just a time snapshot of the field created by a Dirac in space and time at this location here. So in space is located here. It fires at time t is equal to 0. And you look at the field at time t is equal to something, t is equal to 1, let's say. So this is in a homogeneous medium. So the what you're observing here is essentially a Gaussian. And the field lines or isotherms will look like circles because it's a homogeneous medium. So there is no inclusion whatsoever in here because the field lines look like circles. Now you drop in an inclusion. This inclusion in here corresponds to having a homogeneous Dirichlet condition, or simply put like temperature 0, like you drop an ice cube in there in that plate that you're looking at the temperature of. And you will see that the field lines now, they don't look like circles anymore. And you could use this to, if you're observing the temperature somewhere away from the inclusion, to tell whether there is inclusion or not. Of course, there will be probably people in the audience that know better ways to do this and image this, but that's not the main point of the talk. The main point of the talk is how can we somehow hide this inclusion so that I cannot detect it if I'm outside of some cloaking region. And the way we're going to do this is using a distribution of heat monopoles and dipoles. So on some surface to control the temperature inside a domain. So the way we're thinking about doing this, is using Peltier devices or Peltier elements. So these Peltier devices, they're thermoelectric devices that when you run current through a metal-metal junction, it transports heats from one side, let's say this is the cold side, to the hot side. So you flip the polarity and you can flip the direction of the heat flux. So I made a little cartoon of this here with these boxes, so adjacent boxes. So there is a blue box and a red box in here. And this means that the flux will go in the direction normal to the interface between these two boxes, okay? So I have two kinds of Peltier devices in here. So I have some that will transport heat across the plate. So I'm thinking of this domain omega to live in some plate. And there are some devices that will bring in heat or take out heat from the plate to some exterior domain. So I need this. This will correspond to the monopoles if you were living on just the boundary of omega. I need this because there's no free launching here. I'm not, violating any laws of physics. If you wanted, for example, to set the temperature to 0 inside this region, and it was hotter outside, then you need to take that energy out somewhere. And that's what the monopoles will do. So in our imagination, at least, this could be done with Peltier devices. You'll actually see a picture of somebody who tried to do this for the steady state heat equation. Here we're doing it for in the transient regime. So we're I'll show you that in a second. Okay. So also, please, if you have any questions, feel free to interrupt me or put it in the chat. And now I have the chat window opening here so I can see any questions in there. All right. So this is not the only way of cloaking, of course. There are passive cloaking strategies. That means that they don't use energy. I mean, in order to operate these Peltier devices, I need to run a current, so I need to spend energy just to transport that heat from wherever I want it to wherever I want it to be. So there is approach that is classic now in transformation optics, which was discovered by Greenleaf, Lassas, and Ullman, and then independently by Bentry, Schurig, and Smith. Even if you could argue that Greenleaf, Lassas, and Ullman did not look at it as cloaking at the beginning, they came up exactly with this idea of by looking at an inverse problem, the not uniqueness for the Calderon inverse problem. So the way this works is that you do a transformation of space to create an anisotropic medium that will work like a piece of homogeneous medium, but with a hole in it where you can put things in it. So the effect is that you have if you had rays, for example, this rays will be bent around the region to be cloaked. There is also a method of anomalous resonances where you exploit some resonance that happen close to negative index material, complementary media, which also uses negative index materials. And these methods and others that I haven't put in here, this is a very incomplete review of what's going on, of course, in cloaking. It applies to a variety of wave phenomena, acoustics, elastic waves, seismic waves, there's water waves as well, and even diffusive phenomena. So there are anisotropic or cloaks out there for the heat equation, which is the main subject here. Now, what about active cloaking? So the principle is to trade, using exotic materials that may be anisotropic, hard to fabricate, and use exotic sources, right? So exotic sources of whatever fields you are working with. This was realized by Miller in 2006, who observed that if you use Green's identities, you could obtain perfect cloaking. That's the name of his paper, on perfect cloaking. There are the advantage is that you can do other things, not only cloaking, but you can do illusion and mimicking of objects or sources. The drawback is that you need to have some information about the incident field. This is not something that you need when you're doing the passive cloaking, like the transformation, like the classic, let's say, transformation-based approach. You don't need to know what's coming in. It's guaranteed to that for any field that's coming in, that piece, that the cloak will look like a homogeneous medium. So it will hide whatever is in here. Here, we do need to know what the quote-unquote incident field is. So we worked in the past with the Laplace and Homos equations with Graham Milton and Daniel Onofre. And our objective in there was to use this idea by Miller, but make it into active exterior cloaking, meaning that if you just use Green's identities, which is what I'll be doing for the heat equation here, you enclose the cloak region completely by sources. Here, instead of having infinitely many sources, we just have 3 or 4 sources, let's say, and we show that that's enough to cloak a region. This approach was also successful for elastic waves, bulk, and on a plate. And it has been shown to also enable mimicking or illusion problems. So again, this is the problem where I can make an object, an apple, look like an orange, let's say. All right, so this actually has been implemented for the Laplace equation. These are pictures from papers that have implemented this for the Laplace equation modeling conductivity in a fluid. So what you see here is a printed circuit board. So this is the back of it, and this is the front of it. And the front of it sits at the bottom of, let's say, a water bath. And water, well, conducts electricity. Maybe you need to add a little bit of salt to it. I don't know. And these little dots in here, they correspond to electrodes that you can activate. You can throw in currents in there, set voltages, you know, at will at all these different points. And with that, you can do active cloaking for the Laplace equation. In this other implementation, this is also Laplace equation because it's a steady state heat equation. What you have is a plate that conducts heat. And there is one end of the plate that is set at a cold temperature, let's say 5 degrees Celsius, and the other end is at a hot temperature, let's say 60 degrees Celsius. I believe that maybe, no, if you look at this scale, yeah, it's 60 and 5, between 5 and 6 degrees Celsius. And of course, if you don't have anything on that plate, if the plate is completely homogeneous, the field lines or isotherms, they will look like lines like you have in here, parallel to the sides. If you drill a hole into that plate, then you'll see that the field lines are disturbed by that perturbation, and you will be able to tell there is a hole in there from thermal measurements made on the plate. And what Nguyen and collaborators did is they put a bunch of Peltier elements on the surrounding that air hole, and they were able to adjust them in such a way that the field lines look straight. So this is cloaking, but it's cloaking for the Laplace equation. It's cloaking for the heat equation, if you want to say, but it's for the steady state heat equation. We work here with the approach that I'll show you, work with transients as well. Okay.
May I ask a question?
Yeah, sure.
So those heat and those temperature diagrams, that they're taking at any fixed time, or
this is steady state. It's steady state.
After
so
a long
they just wait until everything settles, right? So they put the plate between, you know, hot end and cold end, and they wait sufficiently long until the steady state heat distribution, which will look like X2 if this is X2 direction, settles in.
All right, I understand. Thank you.
Yeah, sure. All right, so the model we're going to use in here is just the classic heat equation. So we have time derivative of U, which represents a temperature, is equal to K, which is the thermal diffusivity, times Laplace U plus some source term H in here. And I said an initial condition U naught. So of course, the green function fundamental or fundamental solution for the heat equation is well known and is given by this Gaussian function. It turns out to be 0 when t is negative. That's important because of causality. And this function will be smooth essentially everywhere. So if you look at it in time and space, the only place where this function is not C infinity is going to be the origin of the time and space plane or Cartesian product, okay? Fine. Now, let me introduce a couple of fundamental problems in here just to put things in context. So I'm not talking about cloaking, but these are the two tools, or mimicking yet, but these are the two tools that we're going to combine, let's say, to get cloaking, mimicking of sources, objects, and so on. So the first problem is what we call the interior reproduction problem. And if you give, what it says is if you give me a solution U to the heat equation, let's say on some domain that contains omega, and it's a solution to the heat equation with no sources, meaning that the source term is 0, then the question is if I can find some distribution of monopoles and dipoles on the surface in here, such that I can get that solution of the heat equation in this yellow region, and then 0 outside. The 0 outside is important because we don't want to, we want to be manipulating fields inside of the region omega, but we don't want to mess up whatever fields we have outside of omega. This notation in here, whenever we do an interior reproduction problem, there will be a U of omega And the associated problem in the exterior, we'll use a V for that. That may be a little bit confusing, but it should be clear from the context which problem I am solving anyway. So for the exterior reproduction problem, I assume I have some solution of the heat equation in some domain that contains the complement of omega. And the question is, can I reproduce this field in this yellow region, and of course to infinity, from adjusting monopoles and dipoles, let's say, on the surface in here. So these problems can be solved by using essentially Green's identities. This is a very well-known identity for the heat equation in here. So let me parse it because there's a lot of things going on in here. So I have two terms in here. The first term is a term that integrates over time some boundary integral. The second term is a term that integrates only in space in the domain omega. And the claim is that whenever you evaluate these two integrals, the function that you get is identical to u inside omega, but 0 outside of omega, okay? And again, the assumption in here is that u is a solution, a solution to the homogeneous heat equation. So in the first term, what you see is a bunch of sources. So whenever you see G in here, this is really the field corresponding to a point source that is localized at Y and that fired at time S, okay? And you're observing that field at time T and at location X, okay? So what this term is computing is what will be the contribution from all these sources firing in the past of time T, of the present time T. And these sources are weighted somehow by the either the normal derivative of the field that you want to reproduce or the value of the field you want to reproduce at that time S. So if you know all that history of the fields you want to reproduce on the surface of the domain omega, then you know how to calculate or do this term. And this corresponds, by the way, to roughly to what happens with the Peltier devices, right? Because this thing here, this term in here, this dipole term will correspond to the Peltier devices that I showed earlier in that cartoon, and it will transport heat across the boundary of omega. This one here will transport heat from wherever omega leaves to somewhere else. No? Okay. And this tells me how to modulate in time those Peltier devices, okay? And it's all causal because I'm only using things from the past. The second term in here, it's simply a bunch of point sources that are firing at time t is equal to 0, and that correspond to the initial condition. So you're just observing the effect of that initial condition later in time. Just to give you a little bit more intuition of what is going on in here, I'm going to apply this reproduction formula to this very boring solution to the heat equation. It's actually steady state heat equation solution x2, meaning that it doesn't change with time, right? It's a harmonic function, so it solves the heat equation. So on the left is the purported result. So I'm applying this for omega being a disk. So you see that the field lines look indeed like consistent with x2, and I have 0 outside. White in here is 0. This is probably x2 plus something, or the origin is shifted so that I don't have to deal with negative temperatures here, and at least in this on the left. And then I'm showing here the contribution from the boundary terms. So this time history integral going on in here, I'm not putting it, and from the volume integral terms, which involve the initial condition. The initial condition in here is simply x2. So what you see here is just x2 blurred by the heat kernel evaluated at t is equal to 0.01. And so as time increases, the expectation is that this term will just diffuse away. But at the same time, the boundary term is somehow compensating for that. this boundary integral term is compensating for that by canceling out everything outside of the surface of omega. That's why you see blue in here, that's negative temperature. So they're canceling out these temperatures in here. And on the inside, they're just compensating for this not looking like a straight lines by adding something else. That's the effect of this. So let's just see what happens if you increase time. So here I increase time by a tiny bit, and you see indeed this term diffusing away. And this term also creating something that will cancel out that field. And in the inside, you should see as time advances that the field lines start getting more and more straight, meaning that as this term goes to zero, well, the term is whatever you're reproducing in here will look like what we wanted, like x2, okay? So these are the two things in here. This is just to show you how initial conditions would be included in this. I will be ignoring initial conditions later on. Which is here, for example. So now you can write this with the language of potential theory. So you define two operators, S and D, a single layer potential, double layer potential. These are like your classic single and double layer potential for the Laplace equation. The difference is that you're integrating a history of all these things from 0 to t, correct? So the single layer potential in here just, again, integrates some weight in time and space on the boundary, in the boundary cross time, times the Green's function. Double layer potential does the same thing times the normal derivative of the Green's function. And so that reproduction formula can be written in a more, let's say, succinct way in this fashion. So I need to know what the normal derivative is of the field on the surface and what the field is at the surface in order to reproduce this field inside of omega. If this initial condition is 0, right? If the initial condition is 0, then this volume term here goes away and I don't have to worry about it. Okay, so let me show you a numerical experiment for this introduction, for this interior production formula. So on the left in here, you see the temperature that was created by firing a point source at time t is equal to 0 and located somewhere around here where my mouse is. I'm just looking this at times equals 0.2. So again, this looks like a Gaussian. This is applying that interior reproduction formula. So I'm just integrating those monopoles and dipoles for all past, t's on whatever these points here. So this looks like crosses normally. Maybe you cannot see them that much in here, but it's on the boundary. And indeed, you see that the field outside of this region is 0 and the field inside looks like the field that we want. Here is what the error looks like at that very particular time snapshot, t is equal to 0.2. And it's interesting, the error looks bigger on the boundary of omega. This is still true, even if you look at the maximum for a bunch of times. By the way, the scale here is logarithmic. So the error inside here is 10 to the minus 4. That's 1/100%. So it's a pretty good error for considering the very, poor discretization choices that we did in here. It's a very good error to have. Okay, and I can talk about more how we did this, but that's not my main goal today, but I could talk about it later. Fine, so this can be explained actually by simply applying the maximum principle for the heat equation. So what it says, so here I have a representation of this, which is a heat time, space-time cylinder. So what this says is that if you want to look at the difference of two solutions to the heat equation on this space-time cylinder, the maximum should occur on the surface of the space-time cylinder or the bottom of it. So that's the bottom of it is this omega here at time t is equal to 0. So the bottom here corresponds to time t is equal to 0. So that's the bottom, and this is the sides of the cylinder. Of course, if you assume that your initial condition is harmonic, then you can use again the maximum principle to say that to eliminate the maximum being inside omega here at the bottom, and it will just be on the sides of this cylinder. That's good, and it's consistent with what we observed in here. And the reason that it's consistent is that whatever we're computing here is just evaluating some solution to the heat equation. By definition, that's what we're doing. So we can compare this to what we want inside this region, and we will get that the error should be at the maximum at the on the inside of this boundary.
May I ask a question?
Yes.
Can you go to a previous slide? Thank you. So what are you exactly comparing here? The right diagram is the result of putting the dipoles on the boundary and measuring what the steady state solution is. And the left one is just firing a point source and measuring the temperature in the ambient space.
So, okay, so I thank you. I think I botched the explanation in here. So this is, I'm showing just you, I'm just showing a time snapshot. This is true for all times between slightly more than 0 and t is equal to 0.2 in here, or 0.5. We can run this as long as we want, and we'll be able to still reproduce the solution to the heat equation. The comparison here, I didn't explain what am I comparing this to. I'm comparing this solution that I'm getting here numerically to what I'm supposed to be getting. So what I'm supposed to be getting is this u of omega, which is defined to be exactly equal to u inside of omega and 0 outside, okay? So there will be a mistake because we integrated this numerically, so there's mistakes in there. But whatever I am plotting here is still a solution to the heat equation. So this is the error just at that time t is equal to 0.2. And this is the error, maximum error on a small time cylinder here, space-time cylinder, where the time here is between 0.2 and 0.5. Does that answer your question?
I'll have to think about it.
Okay, so so think of this as movies, and I'm just showing you one frame of the movie here, and the error between one frame of the movie and what I should be getting. That's this, and this one here is really the error on a bunch of movies in the future from 0.2 to 0.5.
Are you working over the same disk? Because I don't see a disk in the left picture.
So on the left, this one here?
Yeah.
This is just the heat equation solution snapshot that t is equal to 0.2. That was originated by a point source at this location. That's all this is. And then I'm defining this disk in here, and that's the disk omega where I'm going to apply this interior reproduction formula. So that's why there's no disk in here. All my goal in here is to just show that if I apply this interior reproduction formula, then I get indeed whatever this field is in this region and 0 outside. That's my goal here.
Oh, I see. That picture on the left is supposed to be the picture on the right, but you're just cutting out that portion.
It looks, yeah, it looks like I just copy pasted a circle here, but it's really what came out of the numerical experiment.
Well, it's good that they look similar.
Yeah, and this is the error between them. So they are indeed similar. Okay. So explain already the maximum principle. Now what happens outside? So outside, the question is, and this is where there's some math in here. It's that, well, apart from the maximum principle, of course, is that if you have a solution to the heat equation then you can reproduce it outside of a domain. You can reproduce it outside of a domain with a similar formula using a double layer and a single layer potential. However, you need to assume that that solution doesn't grow too fast. So, or in other words, it grows sufficiently slow. So the way to prove this, so we inspire ourselves from a classic proof of the similar formula for the Helmholtz equation. So that formula for the Helmholtz equation requires you to have some Sommerfeld radiation condition at infinity, some decay of the solutions in here. But what happens in here is that if you, let me explain, maybe backtrack and explain this a little bit better. So what you're doing in here is you have your domain omega, and I am simply truncating the complement of omega by a ball of radius r, okay? So if you apply that interior reproduction formula to this bounded domain in yellow here, you have some term that corresponds to this, inner boundary, the boundary of omega, which is this one here, and that's what I want. Plus some other term that will leave, there will be some surface integral on the sphere of radius r. And so the game in here is to show that that term in here goes to 0 as r goes to infinity, as I make this ball grow. And this happens indeed. And because the Green's function for the heat equation already decays like a Gaussian, then intuitively that means that I can let my solution V grow like the reciprocal of a Gaussian, roughly speaking, okay? So that's why you allow for growing solutions in here, but for the Helmholtz equation, right, the Green's function doesn't decay that fast. So the V has to, satisfy whatever the Sommerfeld radiation condition, okay? So what does it mean for to grow sufficiently slowly? So you get this condition in here, and the condition is simply relates the normal derivative of the solution to the heat equation that you want to reproduce on a sphere of radius r, plus some, something times the solution itself evaluated on that sphere. And I want the combination of these two to not grow faster than a Gaussian. Why do I say that? Well, it's actually a polynomial, a constant times a polynomial and times something that's almost a Gaussian. So we were not able to go up to b is equal to 2. So if you had b is equal to 2, then this exponential of a r squared will be the reciprocal of a Gaussian. I should have said reciprocal of a Gaussian, right? Because Gaussians decay to 0. This is the reciprocal of a Gaussian. Or almost like the reciprocal of a Gaussian. So this condition, although it looks very technical, it is satisfied by many solutions of the heat equation, including Green functions and all their spatial derivatives, simply because these do not blow up at infinity. And the condition that we get in here is no let's say coincidence that we end up getting growth that looks like the growth of the reciprocal of a Gaussian, because that's what you get if you study the uniqueness for the exterior Dirichlet problem. So anyway, I'll get to that in a second, but now let me show you the similar numerical experiment for the exterior reproduction formula. So again, on the left in here, you just have a point source that fire at time t is equal to 0. I'm just looking at the heat distribution, at the temperature distribution at time t is equal to 0.2. And here I define my domain omega to be this disk. And indeed, I can get, by using the exterior reproduction formula, a very good match to the field that I have outside of this domain and then 0 inside. And here you see the error between this calculated field and the field that you should be you should be getting. Here I'm using these because it's exterior. Okay, fine. And again, the error seems to be maximum at the boundary of omega. And same thing in here, the error is still maximum, even if I look at a bunch of different times. And again, this can be explained by the maximum principle. It's in basically the same way. The only thing is that you have to, if you look at the maximum between two, the difference between two solutions of the heat equation, then that maximum should occur on either on the boundary of this space-time cylinder or on this bottom part in here that is crosshatched in red. If your initial condition happens to be harmonic, they can eliminate all this stuff in red and just base yourself on this surface in here. Of course, you need to assume some sort of regularity in here, and the regularity is that the V, the solution to the heat equation, should not grow faster than the reciprocal of a Gaussian, which is also, incidentally, the same condition that you need for uniqueness of the exterior Dirichlet problem. By the way, this is a classic example of non-uniqueness for the heat equation by Tikhonov. Even in one dimension, you can construct solutions. One solution that grows faster than a Gaussian, and another zero. They have exactly the same, initial condition, but you cannot tell them apart. So heat equation does not have a unique solution in that sense, unless you include some condition like this. All right. Anyway,
why is there an error? Why is there a difference in the V1, V2?
So this is just, no matter what the solutions to the homogeneous heat equation. Okay, V1 and V2 are just two solutions to the heat equation. Okay, but what I'm saying is that here, this is one. I want to compare whatever I have outside of this region in here that I calculated here. Okay.
Yeah. I'm asking why is there a difference between.
And I want to also compare it to what it should be. So whatever I have outside here, the true heat equation, these two, so whatever I have outside here and whatever I have outside here, they're both going to be solutions to the heat equation by construction. So I can use this to say where the error will occur.
Okay, and I mean, you get an error because it's not exactly equal?
Because I'm doing it numerically.
And something that you do numerically on a computer is going to be a solution to the heat equation?
Yes. Yes. It's going to be a solution to the heat equation.
All right, that's not obvious to me.
It comes from just from the reproduction formula in here. If you're just summing up these things in here, you're just summing up a bunch of Green's functions, right? So these are going to be solutions. I mean, this is a solution to a heat equation. This thing here is a solution to a heat equation. This is a solution to a heat equation. So you're just summing up these different solutions to a heat equation. That's all you're doing.
Oh, okay. It's a solution in X and T.
Mm-hmm. Okay. Exactly.
Okay.
Okay. Thank you. Let's see. So we are here. So now let me show you how to use this to cloak a source. So this is the first problem in here. So I have my domain omega, and I have a point source that is located at x1, and that fires at time t is equal to 0. So this is what the field will be. So it will be just this Green's function, and I can use the which one is this? This is the exterior reproduction problem to cancel out the field that's generated by the source outside of this region. Okay, so whatever I do to this, I use the exterior reproduction problem. I will get 0 inside, so I won't disturb the field that's inside of omega, but I will get minus u, which is exactly the negative of the field that this source is generating. So when you put the two together, because the linear equation is linear, they will cancel out, right? So inside you will get u, and outside you will get 0. So this is how that looks like. Again, this is, I don't know what that come from. This is a snapshot of the solution of that point source, of that generated by that point source. And this is a snapshot of the solution that I obtained by doing this cloaking scheme. So this, you could think of this as being able to dissimulate the source. And I mean, it could seem that I'm violating some rule of physics in here, but I'm really taking all the energy from this source and sending it somewhere with these monopoles, really. Okay, and this is the error between what I want and what I'm getting, and you see that the error is very small. This is again log scale, so this is 10 to the minus 8, and this is 10 to the minus 4 outside. So it works pretty well. And I have a big error close to the boundary, but that's because the numerical method that we used is not the most fancy one that you can use for this kind of numerical, this kind of time and boundary integrals. But it's good enough to demonstrate what's going on. Here is another problem that involves sources. So what I want to do is I have a source at location x1 that fires at time t is equal to 0, and I want to make it appear outside of this domain as a source that fires at time t is equal to 0, and that is located at x2. It could be at another time actually as well. It doesn't really need to be firing at the exactly same time 0. The domain doesn't need to be a circle, but I'm just doing this for simplicity to illustrate things. And all you need to do is make the active cloak field so that you get x2 outside and minus u1 outside as well. So that will cancel out the field that's generated by u1, and it will set the field to be the field that you will get from source located at x2. So that the result will be having the field u1 inside and the field u2 outside. So let me show you how this looks like. So this is the source located at x1, and this is the source that was spatially located at x2. And this is just a time snapshot of what you would get if you apply this. So indeed, you get, it looks like I copy-pasted this field in here into this disk, and I copy-pasted this field in here outside of this disk. But you obtain this just by using this single and double layer potentials on that boundary. Okay, so that will be mimicking the source, right? Because I'm making this source look like it was this source outside of this region. Now, this is how to cloak an object. So in here, I have some quote unquote scatter. So this scatter for me in here will be something that satisfies the homogeneous Dirichlet condition, meaning temperature equal to 0. And I have a probing field that's outside of the domain omega, and it will be just a point source. Again, point source for simplicity could be something more complicated. That's okay, as long as you know what it is. That's the big drawback of this, of course. So if I know what it is, then I can adjust my monopoles and dipoles on the surface in here so that I get an active cloak field that is minus the incident field inside of omega and 0 outside. And that will give me, of course, the desired result, which would be 0 in here and then something else outside. So let me show you how that looks like. Here. So this is on the left in here, you will see just the point source just diffusing in time, firing in time. This is the object I want to cloak, which is the profile of a known character, and with homogeneous Dirichlet conditions. And in here it's with the active sources. And in the bottom two plots in here, what you will see is what is the scatter field that I get. So as you see in here, the field lines, because there's nothing in this plate that I'm simulating, the field lines just look like circles. When they hit the Homer-Simpson figure in here, because it's at temperature t is equal to 0, you'll see some disturbance of these field lines, and you can tell there is something in there. But here you don't see that disturbance because we are artificially setting the temperature T to 0 inside using these sources outside in here while getting 0 outside. And as you can see, here you have a very significant quote unquote scatter field, and here you have a very small one. So, and this is really a transient phenomenon. This is not just for the steady heat equation like previous work. It's really, so let me put that again. It's really for all times. So you see that I have some mistakes in here near the boundary because the numerical method we're using is a little bit not very precise, but again, it converges really well if you're far away from the boundary. Okay. Anyway, so that's using this method. Let me show you something else now. So this is how to mimic an object. So now if I have this kite in here and I want to make it look like a flower, and I know I can calculate ahead of time what will be the scatter field of this flower that's generated by having this probing field at x1, then I can just set up my sources on the surface to do exactly that. So cancel out the incident field inside this region omega so that there's no scattering from the kite, and at the same time set the scatter field like the one in the flower. And this is a time snapshot of that. Again, but to get these time snapshots, we had to really integrate everything in the history up to time t is equal to 0.2. And in here, what you have is the scatter field only for the kite. So the field lines look very elliptical. Here they look more rounded for this flower. And then when you put the cloak on top, you see that the scatter field from this looks like the scatter field of the flower. So we make this kite look like a flower. All right, so you can also do this in the frequency domain. So that's closer to what we had done earlier for the Helmholtz equation. Actually, you get the Helmholtz equation here as well if you take the heat equation with zero initial condition and you use the Fourier Laplace transform. Then the Fourier Laplace transform of the heat equation will satisfy the Helmholtz equation, but you have a complex wave number now. The wave number here I denoted by kappa so that I don't distinguish it with the K, which is the thermal diffusivity from before. So, and what to do with this? Well, you can still do interior reproduction formulas, exterior reproduction formulas. These are, these will still work. I mean, the interior reproduction formula will work for basically any kappa, any wave number. The exterior reproduction formula, you have to put some caveats to it. If the wave number is real, then you need to use that Sommerfeld radiation condition. If the imaginary part of the wave number is non-negative, then the solutions decay. So you don't need the Sommerfeld radiation condition anymore in here. Once you have this, we can also do think of the same ideas in this active exterior cloaking. So I didn't talk too much about that earlier. So let me explain what that is. So here I have my domain omega. It's a circle, and I just split artificially the boundary of this domain into different segments. Okay, so I have segment partial omega 1, partial omega 2, partial omega 3, partial omega 4, and the what I'm doing here is I'm using some trick, which is called Graph's addition formula, to take all the monopoles and dipoles that leave on this surface, on this segment, and just move them all to X1. There is a caveat to that, but it's not that important right now, but I can, in practice, move all these monopoles and dipoles to this location here. That is not, I don't know how to do that for the heat equation itself. I know how to do this for the Helmholtz equation, but not for the heat equation. If you know how to do it for the heat equation, I'll be very interested in hearing how to do it. But what you achieve with that is that instead of completely surrounding your object by a bunch of sources, you only have, let's say, 4 sources around, and these sources will be more exotic, let's say, but they will still leave gaps so that the object can see what's going on outside, okay? So what we are working on is analyzing this Graph's addition formula, which is very well understood when it converges and all that, but we didn't find that many results when kappa was complex, so we ended up doing our own. And with these results, we can actually predict how fast will be the convergence of whatever series we're using to approximate, all the sources that we have in here. So we can tell you how many terms I need in whatever series I need at each of these locations to reach a particular precision. So that's something that we didn't have before, and we didn't have this before either for the Helmholtz equation with imaginary wave numbers. And of course, once you're done with all this in the frequency domain, you can go back with the inverse Laplace transform to the time domain. So this is, I couldn't resist to show you some very preliminary results for this. So this is actually a time snapshot of a solution to the heat equation. That's the source. So here there's no inclusion. Here there is some inclusion with, again, the homogeneous dirichlet condition, boundary condition. And these were computed by going through the Helmholtz equation to the frequency domain and back to the time domain. And then here are the exterior cloaking for the heat equation. And these devices in here, they generate some fields, some temperature fields that will cancel out the incident field and yet not disturb this incident field when they do that. So they achieve this essentially or approximately the same thing that the Green's identities would do, but just at a few points. And this is just a plot of the error. Anyway, so I'm towards the end. So the summary is that we have an active cloaking method here for the parabolic heat equation. By the way, this also works for mass diffusion or flow in a porous medium. They can also be modeled in certain circumstances with the heat equation. This is active because we needed to use sources to do this, and it assumed that the medium is homogeneous and isotropic. So we are working now on this active stereo clocking. This is what this is, meaning that I don't want to surround the object anymore. And we want to generalize this method also to more complicated media, like media with anisotropy and so on, and see what we can get with that. With that, I thank you for your attention. Here is the reference for most of what I presented today. I'm really grateful to see that so many people came to listen to this. So, I mean, I'm happy to answer any questions or comments.
Thanks a lot, Fernando, for a great talk. So the floor is open for questions. Please unmute yourself. We still have some time for questions. So you had some during the talk, but you're open now.
What was the point of going into the Fourier space with the heat equation?
The point is that we had already worked for the Homos equation, right? And there is a relation between the heat equation and the Homos equation. And with the Homos equation, we know how to quote unquote move sources from one point to the other using this graphs addition formula. It's just some trick that tells you that if you have a point source at this location, I can move it to another location by using multipolar source, okay? This is whatever that means, but
and you're doing
I know how to do that for the Helmholtz equation, but I don't know how to do that for the heat equation directly.
And you're doing something more complicated. You're taking a lot of sources and moving it to one point source.
Exactly. There is a distribution of sources here. I'm integrating all these sources.
Yeah.
And just lumping them into this single device X1, single device X4, etc. That's why when I'm doing this, actually the fields will blow up at those locations. That's why you see this kind of urchins in here, because the fields blow up. What these circles in here that I put in here mean is this is, let's say, maybe where the fields are not that big, maybe just like 10 times. I forgot which level we put in here. Because even if you have a field that blows up in here, you can use the exterior representation formula again to say, well, you know, I don't care that the field blows up inside. I can put a distribution of monopoles and dipoles on this disk, on the surface of this circle in here, so that I achieve exactly the same effect as this urchin with, you know, the interior that blows up.
Right. That page didn't really impress me because outside of the cloaking device, the fields look exactly the same for all three diagrams, including the uncloaked objects and the cloaked object.
The fields look exactly the same?
Or outside of the device. So the whole...
Yeah, this is probably not the best way of
imagine if you made the
preliminary,
object
but
bigger, then the result, the picture would be a bit more dramatic. The difference.
Yeah, it could be more dramatic. You're right. Thank you. It's true, but there is a difference between the incident and the field that you get in here. There's going to be a big scattering. I mean, whenever you're talking about scattering here for the heat equation, it will be something that decays very rapidly to zero. So you need to either to visualize it, either, you know, maybe pump it up artificially to something that doesn't go to zero that fast, or just have a big scatter, which is what we had in the other one. And here we probably just need to put a bigger scatter so that you can see that better.
Wait, so is this for the heat equation?
Yes.
Okay.
This is the heat equation.
Yeah, okay. The one that you don't know how to move the
without going through the Fourier space to frequency domain.
Then how did you figure out how to cloak them? I thought you didn't know how to.
I don't know how to do it directly, but I know how to do it for the Helmholtz equation. So I go to the frequency domain, I do it in the frequency domain, and then I go back to the time domain. But I don't know how to do this directly in the time domain. Like everything we did before, actually, all this stuff in here, this is all time domain. I never ever went to the frequency domain in here. And I don't know if there is a way of moving a source for the heat equation at one location to another location. It might be not good because of causality or something like that. So that might be something that prevents you from doing it. I don't know.
I mean, why would you want to do it only in the time domain? You could just, I mean, it's a perfectly good method to go into the frequency and then do it there.
I want to, yes, but it's just to understand what's going on better, right? This is, why do we do things? Because we want to understand them better, right? So,
yeah, that makes sense.
Fernando, thank you for very interesting talk. I have a question about these elements, Peltier elements. So one question is, how large are they? And then the second is, there should be, so you said that this is coupled, so the elements are thermoelectric.
Thermoelectric, yeah.
So there should be somewhat electric kind of control problem?
Yes, indeed. So I'm abstracting myself from all those problems. I'm assuming that the Peltier devices, when I'm writing these reproduction formulas, that they are infinitely small and they have infinitely many of them, of course, right? So but because even with our crude numerical method, we were able to get really good field reproductions. We think that it might be possible to do even with like the bigger Peltier devices that are available. This one in here is probably maybe 1.5 inches square. And these are typically used for overclocking processors. So if you're into like trying to overclock your processor without your computing going completely crazy, you put one of these things on top and it helps draw the heat away from the processor. Or they're also present in these portable refrigerators that you can plug in your car, let's say, to keep your sodas cool. They just have a little Peltier device in there, and it's completely silent operation to have a heat, heat sink on the outside and on the inside to cool down things. And you don't need any fans or anything. They work pretty well. It's not a very effective way of moving heat around. It's much more, let's say, efficient to do it with the usual like refrigeration with the, closed cycle Freon, whatever. But people have done this, something similar experimentally. This is an actual experiment. I don't know how big this plate was, but probably these were like 1 centimeter wide Peltier devices. And they were controlling them in some way. So what we're giving here is, how do you control these devices so that even with transient heat equation solutions, you can still cloak?
Thank you.
Thank you for this very nice talk. This was very interesting to follow. So did I understand correctly that now all these sources that you were using were like either one point source or a finite amount of point source? So what would be like the trick that you could pass for like sources which are more complicated?
You mean the sources that I use?
Yes, at least in the computation, it seemed that like that all the sources were point sources. So I mean, like, would you have let's say a continuous source in a time?
Yeah, you could. I mean, so this is what we're doing in here. It's essentially doing the boundary element method for the heat equation, actually. So and we like the fact that we're using discrete point sources that we're integrating over, because it gives us really a solution to the heat equation, and we can understand the error in the numerical method using the maximum principle, at least predict where the error will be. That's as far as we've done with the numerics, really, because it's just to demonstrate things. But you could imagine fancier boundary element method techniques where you really have a little, polygonal omega, and in each polygon you have a something that behaves like your Peltier device. There's a distribution of sources. Maybe there is a way of computing that explicitly. I don't know, but that's how you would do it. Of course, everything else. I mean, in my examples in here, everything is a point source. but that is easy to change. There's nothing there. I mean, you can just put a distribution of sources. You can make things like so that they, ease into firing, like the heat up and then cool down. You can modulate this in time and so on, and still achieve the same effect. Again, we need to know what's going on in order to adjust the point sources on this boundary here to cancel them out. That's a big drawback of this.
Okay, thank you. So then about the domain that in these pictures you had like all kinds of domains, like convex and non-convex domains. But are there any restrictions? What kind of domains you can cloak?
So for the scatterer, it's very the scatterer or the inclusion, if you want. This is very general. Essentially, you can, as long as you can find some solution to the heat equation inside of omega that will not generate any scattering from, or any, scattering from your object, then you can cloak that object. So I was working with homogeneous, Dirichlet boundary conditions because it's easy to think of just setting the temperature to 0. But of course, if it was inhomogeneous boundary condition, like 1, let's say, temperature 1, then you have to set the temperature to 1 inside. Right, so that's an easy example, but you can think of other more complicated boundary conditions or objects that will not interact with some particular heat equation field. And if we can reproduce that particular heat equation solution, then we will be able to cloak it. But we didn't really look that much into that. That would be very interesting to look at, I guess. So, what for a particular object, what fields do not give any scatter? What are the neutral inclusions for the heat equation? I don't know about that. That's probably somebody has looked at that, but we haven't. That kind of thing has been done, for example, for the Laplace equation. This is what the Eshelby something, I forget the name.
Okay, thank you so much.
What is scattering? You mentioned scattering.
I keep saying scattering. That's my own, let's say, predisposition of thinking of this problem as if it were waves, even if it's not waves. So I'm really thinking when I have an object like this, let me put this back. The scatter field in here, what I call scatter field, is just the difference between the field that you see in here on the right and the field that you see on the left. So it's whatever the inclusion is doing to the surrounding fields, that's what I call scatter field. So you can find that, by the way, by just solving a solution, solving an exterior Dirichlet problem in this case, right? So it's, if you know that you want the temperature to be equal to 0 on the boundary of this object, then you know from the incident field what the temperature would be in here. And so you impose the scatter field will solve the Dirichlet problem with minus the incident field on the surface of this object. So, I know scatter field is probably not the best way of calling it, but for lack of a better term, that's what I use.
Essentially, it's the effect that the object has on the solution to the heat equation.
Correct.
By placing it into the medium.
Yeah. This is in analogy with what happens with waves, let's say. So, yeah.
Oh, like if you throw like a rock into water, it scatters waves. Like if
yeah, that would be your point. Scatter waves will be when they reflect off, let's say, another object, another like rock in the water.
Okay, yeah. That, I guess that's a better analogy.
Fernando, I was wondering, say you have a little bit of, let's say, a combination or a drift diffusion type of problem.
Yeah. Yes, we want to. That's a very good suggestion, and we're thinking about that. And With drift diffusion, you still can get things like this, but I just want to make sure that there is some physical interpretation to it, you know, something that can be realized, maybe not now, but who knows when, in order to do that problem. But that'll be a very interesting problem. Actually, I mean, this has applications to other places. We have the parabolic equations like what's it called, Fokker-Planck.
Exactly. Yes. Yeah.
Or also the paraxial wave equation. You know, and you can propagate from one plane to the other by solving a parabolic equation. So
that's right. Yeah. Yeah.
Yeah. So these are all places where you could do this. I mean, if someone is willing to do that, it would be really cool to do, like cloaking in fog or something using active sources. This is doable using this.
Yeah,
I guess.
Nice. Yeah, that's a great talk, Fernando. A lot of interesting physics and math here. So thanks again so much. If there are anyone having lurking a last question, there's still a minute. Otherwise, let's thank Fernando again for a great talk.
Well, thank you everyone for coming.